It is really thanks to this stochastic property that one can sidestep the argument of the impossibility of the coupling between classical gravity and quantum matter, and really explore the idea of what if the gravitational field is classical.
The other day, I had the pleasure of interviewing Andrea Russo, a PhD student in Jonathan Oppenheim's group at UCL, who's been working for a while on a new framework to couple classical and quantum degrees of freedom. This might either give us a better way to treat semi-classical spacetime or an actual stochastic alternative to quantum gravity. Enjoy our conversation and remember to let me know what you think about it in the comments down below. Andrea Russo, thanks for being here.
Thank you.
So, 20th century high-energy physics was quite successful in taking classical electromagnetism, making it quantum, and then showing its predictions to be quite accurate indeed. Given that everything except for spacetime is currently described by such quantum theories, it seems rather natural to try to do the same for spacetime itself. So, if the path is so clear, why do we still lack a quantum theory of spacetime?
That's a great question. And I think that the best way to answer is maybe take a little step back to exactly to the 20th century that you just mentioned, to learn a little bit about how we how the entire physics community launched themselves into this search for quantum gravity, right? Because if you go back to the 1950s, once the framework of quantum mechanics was accepted and people were starting to develop the quantum version of previously known theories, the view about the quantization of gravity was still, like, the community was still a bit agnostic about it, right? And it was actually Bryce DeWitt in a paper in 1953 who really brought the problem that having a classical theory of gravity while we have a quantum theory of matter, he brought the problem to the attention of the general community, because his point was, if the stress energy tensor, whose in Einstein equation is actually a quantum operator, so if matter and energy are quantum, we need to describe them with a quantum stress energy tensor. Well, that is an operator, it cannot be directly inserted into Einstein equations. And so what people would do is they would take the expectation value of this operator. And those are the so-called semi-classical Einstein equations, right? And what DeWitt pointed out was that this equation was problematic in the sense that if you take the expectation value of this quantum operator, then as you go to update your quantum state, the Schrödinger equation becomes nonlinear. And this is, of course, a big problem for quantum theory, where linearity of the evolution in the state is quite important. And so that really woke the community up a little bit. And then a few years later, in 1957, there was this big conference known as the Chapel Hill Conference, and the topic of quantum gravity was debated. And it was Feynman who came up with a really clever argument, which was then improved upon in the years after, about why do we need to quantize gravity. The idea is, if you assume that gravity is classical, then according to general relativity, then space-time, a classical space-time, couples directly to matter and energy, right? And so now assume that you're doing a double-slit experiment, right? A famous double-slit experiment in quantum physics, in which the particle, you don't know which slit it goes through, and creates an interference pattern. But now, this time, you're measuring the Newtonian potential that this particle creates and it interacts with. And because gravity in this thought experiment is classical, then you will be able to measure, in theory, this Newtonian gravitational potential arbitrarily accurately without disturbing the particle. And so you will learn things about the quantum superposition, for example, which slit the particle went through, without disturbing the system, which means that either there will be no interference pattern, or you violate the uncertainty principle. And so, assuming that the interference pattern is actually seen and the uncertainty principle is not violated, then you need to quantize gravity. And a little, like a subtle thing to say is that you don't actually, I mentioned us measuring the gravitational field, but you don't need to do that. It would be the actual gravitational field that measures the particle by being directly coupled with it.
So if I can try to recap Feynman's argument,
Yes.
and please stop me if I'm wrong or if you don't agree with me.
Absolutely.
Just to say it in other words, we all know that in quantum mechanics, properties can be superimposed. In particular,
Yes.
particles can be in superpositions of different position eigenvalues, as we call them, right? Be in two places at once, even if this way of speaking
That's
about it is slightly misleading, but I'm sure our audience will be fine with it. Now, if your particles couple to a classical gravitational field, and in this sense you don't need general relativity, you just need Newtonian.
No, I think yes, absolutely.
Okay. You will somehow manage to extract information about your particle state without directly measuring them, just by interacting with their gravitational field, which is 100% classical. So you'll somehow manage to destroy the interference without interacting with the particles, like perform a measurement which is slightly indirect, right? And which should in
Yeah,
a sense
because
happen,
yes.
right? Because so the puzzle there is why we see interference patterns at all, if gravity is enough for us to measure them and know.
Exactly. As you summarized perfectly, it would be the gravitational field itself that's measuring this superposition, and so you will technically see it collapse. But of course, this does not happen, and so the argument is gravity must be quantum, right? And that set off the search for theories of quantum gravity. And in the past 70 years, as to circle back to your initial question, right, we've seen a lot of incredible different approaches, which you can roughly categorize. There's a good categorization, which I think was invented by Isham, where you think of primary and secondary approaches to quantum gravity. And primary approaches are those who assume that gravity can be quantized on its own, like any other theory, like the electron field. And so in this school of thought, we see things like canonical approaches to quantum gravity, and then loop quantum gravity, and all these spin forms. And these are approaches that did have some success. For example, spin forms are UV complete in the sense that they have a cutoff that's given by this spin form, quote unquote, lattice. Not an expert in the theory. And on the other side, you have secondary approaches to quantum gravity, which really believe that gravity cannot be quantized on its own, but rather a new all-encompassing interactions and framework of all the fundamental interactions should be developed. And the most famous, of course, is string theory. And so also from that, we learned a lot about the nature of gravity and its relation with quantum information theory. But neither approaches has so far reached their ultimate goal.
Just to be clear to anyone who's listening to us at this stage, we have a lot of videos, both on primary and secondary approaches, surely on loop quantum gravity, spin forms, but also asymptotic safety, causal dynamical triangulations and causal sets, and so on, as well as string theory on our channel. So I leave a couple of videos referring to the theories that Andrea mentioned in the first comment to this video. But now, leaving other theories aside, I find quite interesting that even though we have many arguments that seem to suggest that gravity should be quantized, made quantum in the same sense in which we made electromagnetism quantum, or by, as you said, merging it with other forces, introducing a new fundamental object that in some way produces both gauge fields, matter, gravity. We all know that concerning string theory. You and your group at UCL seem to be following a rather different path, right? For me, and
Yes,
I'm not an
indeed.
expert on your post-quantum, if I can call it that way, approach to quantum
Yeah,
gravity,
sure.
uh, you really seem to try to keep space-time classical. Am I correct? And if so, why are you doing that?
Um, yes, you're I would say you're 90% correct. And you're right. It's maybe in a sense, it's very legitimate to ask with so many, even like quite successful approaches to this problem of quantum gravity, why try and not do quantum gravity? And the reason really is that there is a fallacy or a small fallacy in Feynman's argument and this no-go theorem that mentioned that you cannot quantize, that you have to quantize gravity. And the small fallacy, if you let me use this word, is that um, they make a natural assumption which is nonetheless not completely justified. What do I mean by this? They All these no-go theorems, they assume that the coupling between gravity and energy, the quantum matter and quantum energy, is deterministic. And they do so because gravity and general relativity is a deterministic theory. But actually, the coupling itself might not be deterministic. It might have some noise, some stochastic properties. And it is really thanks to this stochastic property that one can sidestep the argument of the impossibility of the coupling between classical gravity and quantum matter and really explore the idea of what if the gravitational field is classical and what are the consequences of it.
So, if I may summarize it, you said there was an argument by Feynman somehow
Yes.
excluding the possibility of space-time being classical. Then you somehow
Yes.
realize there's a loophole in there, and there's a whole spectrum, perhaps, or a single one, I'm not sure about that, of possibilities in which space-time is classical, in which somehow couplings are stochastic, but we'll get there. So you decided to explore that. So that's the point. There's a whole range of possibilities that have not been explored, and you are now trying to explore them.
Uh, in a sense, yes. Maybe let me first say it wasn't me that came up with this idea, and hybrid theories of classical coupling, classical gravity, and quantum matter existed already. Um, However, maybe I can give an intuitive picture of why this works, right? And so we can imagine a scenario in which we have a planet in superposition. So pick your favorite planet and you put it in a superposition, and with 50% probability the planet is on the left, and with 50% probability the planet is on the right. So let's now go through the scenarios. So the first scenario, which is the one that the Witt in 53 told us would not work, is the semi-classical Einstein equation. So if I take the semi-classical Einstein equation and I have a little test mass, what happens is as soon as I let the test mass go, it will go towards the center because I'm taking the average of the planet being on the right and the planet being on the left. And that, of course, is an unphysical situation. This is something that will not happen. Right? What we would expect is that this test mass goes 50% times to the right and 50% of the times to the left, depending on where the superposition is. However, and this is Feynman's argument, imagine that you're looking at the mass, and remember that the mass is a classical, the test mass is a classical object, so you can just measure it. As soon as you see it moving slightly to the left or slightly to the right, you would immediately know if the planet is on the left or on the right. And this is the deterministic coupling, right? The superposition instantaneously collapsed as soon as you have this coupling. However, and this is our line of thought, if there is some noise, so imagine that your classical variable gets some kicks to the left or to the right, like a Brownian motion, so like a speck of dust in a glass of water, then you will need to wait, because as this mass moves, it gets kicked to the left and to the right, and you don't know exactly if it is because of this noise or because the attraction of the planet. So you'll need to wait some time to finally understand where the planet really is. And so your superposition is preserved for some time. And the more noise is present, the longer you will be able to preserve the superposition. Is this clear enough?
I'd say it's clear, and it gives way for us to properly introduce your framework, right? This is an intuitive picture,
Yes.
but I would ask you if you agree to go slightly deeper into it, starting from the very beginning and then trying to explain to us how this stochastic coupling may work, how we should think
Yeah.
about it,
Yes.
might be its source, if there's any, and in general, how we should picture your line of thought.
So I think, I mean, I would say that different members in our group have different ways of thinking about it. Uh, I always like to start by the state, right? Because if you think of any framework like classical physics or quantum physics, one of the most important assumptions that a framework can give you is what is the state. So is your state a point in some configuration space? Is your state some vector in some Hilbert space? And in CQ theory, like in other hybrid theories, the state is a hybrid state. So it's a configuration space or a phase space, depending on what you prefer, where the classical degrees of freedom live. And then at each point of this configuration space, there is a Hilbert space that hosts the quantum degrees of freedom. And so the state allows you to describe a system that is classical and quantum, where the classical and the quantum degrees of freedom are allowed to interact and especially back react onto each other. And so once you have the state, you need some rules for the dynamics, right? And hybrid equations of motion have actually been known since the 80s, so this is not something we also invented. There was great work that was done, but a lot of them suffer from one or another problem. So for example, some of them, I think the original ones formulated in 88, were not completely positive, right? So you will lose the probabilistic interpretation. And some of the latest ones had some like maybe non-locality problem or some non-linearity. So what Jonathan did, then had by Zach and Carlos Paracciari and Barbara Soda, is that they asked what is the most general evolution equation for this hybrid state that is positive, that preserves the probability interpretation, right? And that allows for back reaction and does not mix the degrees of freedom. So the classical degrees stay classical and the quantum degrees stay classical. And so there is a mathematical process you can go through, and you derive a master equation. So it's a differential equation for the evolution of the state. And when you look at this master equation, you immediately see a couple of things, right? You see that it's some sort of generalization of both the Fokker-Planck equation, which in classical physics describe systems that diffuse, so like Brownian motion, and the Lindblad equation, which describes open quantum system that decohere with time. And so you have both the effects, and you look at what happens to your state, and you see that as there's a classical probability distribution over your classical degrees of freedom. It evolves, and there's this noise and there's this diffusion, and at the same time, this back reaction, back and forth from the classical and the quantum degrees of freedom, make the quantum superposition decohere, like makes the quantum state decohere in some eigenvalue.
But in a sense, you have some decoherence, which is expected, but not an immediate collapse as would have happened in
Exactly.
Feynman's thought experiment. Is that correct?
Exactly. That's correct. And I think it's interesting because when you really look at the master equation and you ask for what are the conditions for positivity of the master equation, right? It's important that the evolution of the state is positive and linear. You obtain two relations uh, between the coefficients of these different terms, right? Because we have a coefficient that regulates the diffusion, a coefficient that regulates the decoherence, and one that regulates the back reaction, right? And so by tuning these coefficients, you can increase or decrease the various effects. However, by asking for positivity, you realize that first of all, if the back reaction is not zero, so if there is some back reaction, then you must have decoherence, right?
Okay.
And second of all, you realize that there is an inverse relation between the decoherence and the diffusion coefficient. So the more you tune up the diffusion, so the more noise you put in the system, the less decoherence you have. And we call this the decoherence diffusion trade-off. And it makes intuitive sense because if your system is very noisy, you need to make a lot of measurement in order to understand how your how your quantum state has decohered, right?
And in a sense, you recover Feynman's setting by sending your noise to zero. Is that
Yes,
proper?
in a sense, ideally, right? If you turn the noise to zero, but then what happens is really, if you this equation is really all about handling the back reaction correctly, right? Which is something that semi-classical Einstein equation cannot do, for example. And so if you just shut off the noise, the entire equation doesn't work anymore, really, right? So yeah, so maybe you can't do that directly with the master equation, but ideally, yes, if you make if you lower the noise to very little, then you have very quick decoherence.
Okay,
Yes.
let's say that it morally corresponds, like a very little
Yes, yes,
morally
yes.
corresponds to Feynman's setting. This is extremely interesting, at least according to the person who's hosting this interview. But you
I'm
seem to
glad.
be describing a framework rather than an actual theory of spacetime, right? You've talked about
Yes.
quantum degrees of freedom being coupled to classical degrees of freedom in a way which has this trade-off between decoherence and noise over your classical degrees of
Hmm.
freedom, but your classical and quantum systems could be whatever. Am I correct?
That is very, very much correct. And indeed, the beauty of this framework, in which there's still so much to explore about, is that you are able to pick your classical degrees of freedom and your quantum degrees of freedom and having them interact and study how their interaction and this back reaction works. For example, a very simple system is, we call it the CQ qubit, which is imagining a particle, no, with spin, where your classical degrees of freedom are just the position and momentum of the particle, and your quantum degrees of freedom are spin. And so as this particle evolve, and as this amazing work on this was done also by Isaac Layton, my colleague, and you really see that the particle diffuses in in phase space, and at the same time, if you look at the Bloch sphere where the spin is, there's also a diffusion there from maybe a plus state, so a superposition that you started with, towards either 0 or 1, and you literally see a stochastic then decoherence towards one of the states. But then, of course, the big picture is to pick gravity as the classical system and maybe matter fields for the quantum one.
And in this sense, just to be extremely precise, your classical degrees of freedom don't need to be fundamental, right? You could always have some quantum degrees of freedom from which your classical degrees of freedom somehow come or emerge, or pick the word you prefer depending on your philosophy. But is that is that appropriate?
That's absolutely true, and indeed, then we can get into like a deeper discussion about what's the purpose of this framework, right? And in a sense, this discussion is rightly focused on the big picture of a quantum theory of gravity, but we don't have a correct semi-classical theory of gravity, right? Because, and if you think of some of the greatest problems and greatest papers that came out in the past 40 years, like black hole evaporation or some cosmological work, which were done in the semi-classical regime, they were done using an incomplete semi-classical regime, because semi-classical Einstein equation work well only in a very narrow number of situations, right? And so one thing, I'm not claiming that the results that they obtain are wrong, clearly, but it would be interesting to understand, okay, what if gravity is not fundamentally classical, because maybe, it turns out that it's not. But there is for sure a classical limit in which gravity is classical but matter is quantum. And so what is the correct way of describing this limit? And I would argue, but I'm biased, that the correct way would be CQ. However, you can also take the point that maybe gravity is fundamentally classical, and then in that case, the parameters of the theory are a bit more restrictive, but that could also be possible.
If I understand correctly, this implies that either you can use this framework to, let's say, properly, assuming it's correct, clearly. We
Yes.
always have to work under this assumption. Right?
Absolutely,
And
absolutely.
we get to how to test that, but let's postpone
Yes.
it. As always in quantum gravity, let's postpone it at the end of the
Let's
conversation.
postpone the measurement later.
I'm just kidding. I'm kidding. So this is for insiders, not for a general audience. I apologize. So either this allows you to properly describe settings in which you, for instance, have an interaction between quantum fields and a general relativistic classical, in that sense, black hole, as we have in black hole evaporation, which is a long-standing problem with proposed solutions, different approaches, but clearly having a better way to write that down, even if gravity is fundamentally quantum, would be interesting.
Absolutely.
Or you'll take that with a few restrictions, you said, regardless of what they are specifically, as a fundamental framework, in which you actually describe a classical spacetime.
Yes, exactly.
If we pursue this second proposal approach idea, how should we picture, regardless of your personal, taste in that, can you tell me something about, I'm not everything, not a complete picture, I'm not asking for miracles, clearly nobody has a full picture, but can you tell me something more about the way you might conceptualize an actually fundamentally classical spacetime? Because I'm sure many people have a big question mark above their head right now.
I mean, of course, and in a sense, maybe I would dare to say that picturing a fundamental classical spacetime is much easier than picturing a fundamentally quantum spacetime, right? Because normally when we think of spacetime, we think of it as the background that then Einstein proved it's not absolute, but still as this background structure that is there and allows us to pinpoint events that happen and tells us about how to the background in which quantum fields evolve. So a fundamentally classical theory of gravity would be basically general relativity with some added effects coming from this back reaction with this quantum matter, right? And so, for example, I can tell a bit more. One of my works was to actually, because I talked about the master equation formulation of this framework, but we have other two formulations of this framework. One, it's in terms of stochastic differential equation, so it's an unraveling. Right, so there's a stochastic differential equation for the classical degrees of freedom and a stochastic differential equation for the quantum degrees of freedom. But we also have a path integral formulation of the framework. And so using this path integral, me together with Isaac, Zach, and Jonathan derived the Newtonian limit of CQ gravity, right? So from a full general relativistic CQ picture of a path integral that is actually very complex, right? And there's still so much more work to do to understand it and extract information from it. But we took the Newtonian limit and we recover actually a situation that was described beautifully by Lejos Diosi and Antoine Tilloy in some work about coupling the Newtonian classical gravitational field with the quantum state as a measurement and controlled system. And the effect is that you basically have a Newtonian potential with some noise around it, right? And so what the framework tells you is that there's a diffusion of the gravitational degrees of freedom, but the further away you diffuse from Einstein's equations, the less probable is, right? It's a classic path integral way of dealing with things, right? The more you get away from the equations of motion, the more you're penalized.
My question is just to make sure I understood you correctly. You're saying that if we assume spacetime to be classical and be coupled to quantum degrees of freedom via your master equation, we also need to accept your in the sense of your groups. Clearly, English has this ambiguity of you being
Yeah,
both
you're right. You're right.
Europe. Here's two Italians that come from a place where
Yes.
we have a singular and plural one. I'm always referring to your group. Now, if you buy into this idea of space-time being fundamentally classical, and once again, I'm happy with accepting weird things. Quantum mechanics implies that you need to accept some weird stuff, so I'm absolutely open to that.
Absolutely.
You somehow must accept that there's some fundamental classical stochasticity built into the universe. Is that a good intuition?
I think it's a great way of saying this. Yes, and I think there's a concept that if gravity is really classical, I think I will find that quite enjoyable in the sense that we are so taken by our very human idea of beauty and elegance, and that all has to be unified in one unique framework, then seeing nature telling us again in our face, like it did at the end of the 19th century, hey, things are not at all like you imagine, would be, I think, quite enjoyable for me personally. But yes, the idea would be that through decoupling, because normally you can think of the quantum framework as having some intrinsic probabilism, right? And through this coupling, through this back reaction, there's an exchange. Some of the intrinsic probabilism of quantum mechanics, of the quantum framework, leaks into the classical degrees of freedom by, creating this noise which makes probability distribution instead of well-defined classical state. But also the opposite happens, right? Because some of the intrinsic determinism of a fundamental classical theory leaks into the quantum degrees of freedom, and it measures them with time, making them eventually collapse in a well-defined state.
This is absolutely compelling, and thanks for the great clarity and explanation. Now I need to get to the experiments, right? And I assume the topic will touch not only on post-quantum or stochastic spacetime, but to your framework in general. For instance, the classical quantum qubit you mentioned before. So, do you have any experiment in mind? And with you, once again, I mean anyone who's working on this. Do you have any experiment in mind to try to test this coupling?
So I think that actually one of the appeal of this framework is really that it appears to be much more easy to test with respect to proposed quantum gravity ideas, which, for example, if they were to find that gravity can build entanglement, right? then that will demonstrate the nature of quantum gravity, like, and that would of course discard the CQ theory as a fundamental theory of classical gravity. Nonetheless, I think that's important too, right? Because a loophole in Feynman's argument, let's call it like that, exists. And so this loophole ought to be closed somehow, right? And so it will still be an advancement, I believe. But yes, how do you test a CQ framework? Now, as I mentioned earlier, we have these constants that regulate the diffusion and the decoherence, right? And we often work in a version of the framework where there is a saturation of this inequality between decoherence and diffusion, in the sense that the decoherence constant is exactly 1 over the diffusion constant, right? And so that, of course, turns two constants into one, right? Because you can write one in terms of the other whenever. And so what you can do is you can do diffusion experiments, so measure gravitational interactions, for example, with a torsion balance, to put an upper bound on the diffusion from that side, and then you can do decoherence experiment and measure what's the decoherence time to put a lower bound on the diffusion. And so you squeeze the parameters of the theory and see if some models are ruled out or some are ruled out or not. And just to conclude, there's actually there's a bit of freedom in the choice of these coefficients, and there's a lot that we still have to explore about them, because in the simplest version you can think of, you could just take them to be constant, but they could have some space dependence, right? They could have some dependence on the field, even if a dependence on the classical degrees of freedom maybe would not be optimal for a fundamentally classical theory. But still, you can rule out different models with experiments. And so, yeah, hopefully these experiments will be done soon. And with the experiments that exist already, we put some tight bounds on some of these models. I think one of them, well, we thought to be completely, like the simplest one called the ultra-local model, we thought it to be ruled out, but now maybe it turns out it might not be. But you can rule out modern, absolutely, without building billion-dollar accelerators.
Just to make it clear to people that might not be into the field, what Andrea is talking about, and once again, please stop me if I'm wrong, is that whenever you have a framework depending on some numerical parameters, numerical constants, assuming them to be constants, because you rightfully
Yeah,
pointed
but
out
still some parameters.
some parameters, let's be agnostic in that sense. Your experiments allow you to rule out some portions of this parameter space, narrow the zone of it, which is compatible
Yeah.
with experiments. So this is the idea. You have this landscape of possible parameters in which any point in
Yes.
your landscape, your hills and mountains corresponds to a specific configuration of parameters, and you start ruling them out, like eliminating portions of the territory until you get a very small portion, and you know that if the theory is correct, it must sit there, right? Nature must sit there.
Absolutely. Yeah.
More or less the idea. So I would thank you for having explained it to us in such a, once
Oh,
again,
you're
clear.
welcome. I hope it was clear enough.
It was, it was. If I may, I would now ask you a couple of more personal questions. You
Yeah,
were not
sure.
prepared to this, but you are free not to answer if you don't want to. Why physics? What led you into physics in the first place, and then in quantum gravity?
Yeah.
This might be really helpful for a young audience.
No, absolutely. Well, I think I mean, in my high school, I always liked physics and maths. Not that that is a requirement, of course, but it was helpful. But really, I remember quite clearly the reason why I got into, like, when I started really thinking about doing physics, which I think I was 15 or 7 or 16, and I was playing a video game at the time. And in this video game, they mentioned there was this alien invasion, and they mentioned that they were coming to Earth through Einstein-Rosen bridges. And I had no idea what that was, so I Googled it, and I thought, wait a second, this is actually science. It's not just made up things. Um, and so then I looked a bit more into it. I found some videos about quantum mechanics, and I had really great high school teachers that really encouraged me to pursue this passion. And then I moved to the UK to study.
Thank you very much. Thank you very much. And do you
No
have any
worries.
suggestion? Because I think that young researchers are a great bridge between students and seniors. So you might have some good suggestions for younger students that want to get into theoretical physics, quantum gravity in general, or
Yes.
your approach in a
Yes.
specific way.
One thing that I really feel I'm much more oriented towards giving practical tips. Like, of course, you should not be discouraged and keep trying, and that always goes through. But one thing that would have really helped me is that when I was, for example, an undergraduate, I tend to focus just on the subjects that I found really interesting, right? So I went into a physics degree knowing that I wanted to study gravity and fields and particles, and so I tend to kind of discard a little bit other courses. And then later in life, especially if you want to be a theoretical physicist, you realize that everything is important. It could be thermodynamics, it could be electromagnetism or solid state. There's always something, some technique, some way of thinking about things that comes up when you're looking especially at such an all-encompassing problem like quantum gravity. Yes, that's definitely one advice. And the other is to try and study things on your own too. I do not be discouraged by the fact that these are very advanced topics. Physics is learned mostly by repetition. And so you study something, you understand 10%, then you study it again in class and you understand 20 and then 30, and then some topics I feel like I understood last year and I'm at the end of my PhD.
In a way, your first suggestion might be summarized as before becoming a good quantum gravity physicist, you need to be
Yes.
a good physicist, right? Which
Exactly,
means
exactly.
overcome all the
I think that's a great way of putting it. Before wanting to do things, you need to learn how to observe what's already been done, right? Because it's there for a reason.
And with this good advice, I thank you again for having spent your time with me. I remind all our nice viewers, while I thank them too, to subscribe to this channel and take a look at the other things we uploaded on it, because there's a lot of material on quantum gravity, on its approaches, and on more general topics. So,
Perfect.
Andrea
Thank
Russo,
you. Thank
thank
you,
you very
David. It
much,
was a great interview.
and see you soon.